say your name, what your major is, what level you are.
Okay. My name is JD Barrera. I'm an electrical engineering student here at Texas A&M. I am a senior, currently going into my last semester before I start graduate school.
And what is your project on today?
My project is something I did for RU, Research Experience for Undergrads this summer. It's titled Frequency Agile Substrate Integrated Wavguide Bandpass Filter using nanoparticle dispersions.
And what does that mean for a layperson?
What does that mean? Right, yeah. So basically a substrate integrated waveguide is this new RF and microwave device topology that's coming out that's actually incorporating all the advantages of a regular rectangular waveguide and putting them into planar form. Since most RF and microwave devices are in planar form, it's hard to make that transition from this big clunky metal object. So if we could already place it in planar form, that's great. So we do that using these vias.
Okay. So the advantages are that it makes it smaller.
Yes.
So you can put it into a more confined space.
And you preserve the advantages of a regular rectangular waveguide like high Q, low electromagnetic interference from outside signals, things like this.
So I'm going to scoot in here a little bit and explain what each part of your poster board and what you did.
I'm going to start off here. So like I already talked to you about a substrate integrated waveguide. And in order to make this a bandpass filter, what we basically did was put two posts in the center of this waveguide. This created a cavity within the waveguide. A cavity is basically a microwave. It's like a microwave that resonates at one frequency only. So basically we input this signal through here, we hit this cavity which says, okay, we can only have one frequency go out, and it shoots out just one frequency, which is basically your bandpass filter. Now we tapered this transition to basically impedance match it. It's a pretty common circuit term to preserve power transmission. We fed it with your basic 50 ohm microstrip line, and like I said, we created this bandpass filter. And the length between these two posts, you getting that? The length actually determines what frequency the cavity is operating at, or what frequency your bandpass filter is operating at.
Can you change that?
Yes. You can change it through simulation pretty easily, right, by typing a new system, but physically it's hard to change that. So what we do it electrically by adding in this post right here. So basically we drill the post, and we covered it with a copper mesh screen, and we were able to put different materials in it. So basically we're perturbing this material within the substrate, which changes things electromagnetically with the electric fields within the substrate, causing these two posts to seem electrically longer. So this is basically like your guitar, right? If you plug a guitar, you're operating at one frequency, you're hearing one sound. Now if you shorten that guitar string and you pluck it again, that's a totally different frequency, totally different note.
So you're changing the length, not physically, but using electrical properties.
Yes. Through material properties. So that's what I'll bring you down here. So we use a nanoparticle called BSTO. That's a snapshot of it. It's actually about 100 nanometers in diameter. It's a really small particle. And the dispersions are governed through this. Basically we have this fluid reservoir, which is oil. And we input our nanoparticle in this. They effectively mix together somehow. They introduce new material properties. We use a mixing rule called the Maxwell Garnett mixing rule, and we get this effective permittivity through it. So this is the mixing rule, which basically says you have a effective inclusion permittivity, which is your oil, which is your BSTO, an environment permittivity, which is your oil, and a volume fraction of your BSTO coming in. And through this, we get an effective permittivity of that substance. So this could actually be adapted to use discs, needles, and spheres. In our case, we use spheres. Alright, here. So like I said, it could be adapted to use discs, needles, and sphere nanoparticles. In our case, we use spheres. Now you have different regimes of this, because if you think about putting a bunch of marbles in a beaker, you reach a theoretical limit on the volume fraction of those marbles, right? Same thing as the BSTOs. So that limit is a 74.5% volume fraction. Now to overcome that, you can use different size spheres, meaning that you're filling in all those spaces and you could reach into this regime of reconfiguration. Our project only did a 50% volume fraction, did 25% and 50% volume fraction, which is basically along this curve here. And now we've observed this sort of reconfiguration potential. We started at X band in our air base case, and we reconfigured all the way down to 9.5 gigahertz, which is about 2.5 gigahertz reconfiguration, which is amazing, considering we only use a small fraction of what's out there. And our measured results do agree with this in that the frequency reconfigurations are around the same. Now the performance of the filter itself is actually degrading. This was due to the fact that, of the probes that we're using on our fabricated version. these two clamps were causing a lot of electromagnetic interference. So we removed all these clamps, and we basically got rid of these unwanted modes in the system. We also we used a better soldering job, and we got rid of this mode right here. So basically, we almost
tiny
little things made a huge difference. Now we weren't able to update the results, unfortunately, because posters cost about $75 to print.
That's understandable. You're a college student. You don't have a lot of money to spend on posters.
I hope everyone will take my word for it. But basically, this was just a small stepping stone into my future work. I'm going to be going to grad school in spring, and I'm going to be working on the project I'm going to work on is reconfiguring nanoscale antennas. So basically, this was a stepping stone towards this because we're going to eventually change this from the gigahertz range to the terahertz range. And at that range, the device will actually be a nano device, and we won't actually be flowing fluid through there. We'll literally be inputting particles one by one through there.
And what are the typical uses for something like this?
Typical uses are for any type of filter, are basically noise reduction. Anytime unwanted frequencies are there, noise reduction in general is a big one.
Signal processing.
Signal processing, communications, NASA, communications through space. Endless.
So this program has kind of spurred you on to do graduate school.
Yes, very much so. Yes. Well, I think any type of undergraduate research you could do is phenomenal. Like I tried it this past semester. I loved it. I decided to go to grad school. I had never planned on going to grad school. Never planned on doing any of that. So that was really great.
So one last thing, tell us something that you learned by doing this project, something maybe you didn't know beforehand that after going through it, you learned something new, something that you hadn't experienced.
I had never experienced getting like results like this because in my past research, we worked hard and we got results that we were exactly looking for. And so figuring out what was going wrong here actually was a 3-week process of literally testing after testing after testing. Dr. Huff, my advisor, had left for 2 weeks. He had won an award, so I was literally by myself just testing and testing and testing. And I wasn't able to figure it out by myself. Dr. Huff had to come back, and kind of point out that, well, maybe this and maybe this and maybe this, but I know just, that kind of experience, because that's what a lot of grad school is. I think it's a lot of failures, but, if you learn from those failures,
So you've learned that research, there's a lot of points where you can get stumped in one thing for a long period of time.
Exactly. But I think that's like anything else in life, too. I mean, you just got to overcome that. So.
Well, thank you for your presentation.
All right.
Enjoyed
Thanks
it.
a lot.